Good day. The topic we are treating today is Sum to Infinity 2 by Monserrat. This video is the continuation of the video titled Sum to Infinity. In this video, the solution of the examples that are not solved in the video Sum to Infinity will be obtained. Also, the viewer of this video must have watched the previous video Sum to Infinity for easy understanding of the solution of these examples. So now we move to the solution of the examples. We'll start from the second example to the seventh example. So these are the examples. Now we move to the solutions of this example. Example 2. From the question, we were told that the sum to infinity of a particular geometric progression is equal to 2 of its first term. As we all know, the first term is usually represented by A. So the statement of the question is written here, S infinity equals 2A. This implies that you write down the formula for sum to infinity, which is A over 1 minus R equals 2A. So here we can cross multiply. We have A equals 2A multiplied by 1 minus R, and then we'll divide both sides by 2A. That is why we have A over 2A equals 1 minus R. Here we cancel A. We are left with 1 over 2 equals 1 minus R. So in the question, we are to obtain the value of the common ratio, which is R. So now we make R the sum of formula. R will now be equals to 1 minus half, and 1 minus half will give half. Therefore, the common ratio of the geometric progression whose sum to infinity equals to twice its first term is half. So that solves the second example. Now we move to the solution of the third example. In the third example, we were given the value for a sum to infinity of an arithmetic progression to be minus 1 over 16, and the value for the first term, A, to be minus 1 over 8. So we are asked to obtain the value of the common ratio of that particular geometric progression. So here we can see the value for the sum to infinity has been given, and we have the value of the first term of that geometric progression. So now we write down the formula for sum to infinity, which is A divided by 1 minus R. We are given the value for sum to infinity to be minus 1 over 16. So we substitute minus 1 over 16 equals the value for the first term, minus 1 over 8 divided by 1 minus R, which is the unknown. So we can cross multiply. 1 minus R will multiply minus 1. And you know, if minus 1 multiplies 1 minus R, we have R minus 1. Because we have minus 1 multiplied by 1, we have minus 1. Minus 1 multiplied by minus R changes to plus R. So we have minus 1 plus R, which is the same thing as writing R minus 1. So 16, we are left with 16 here. Since we carry the minus along with 1, we are left with 16. 16, we cross it to this side. We have 16 multiplied by minus 1 over 8. 8 Here 1, 8 in 16 we have 2. 2 multiplied by minus 1, we have minus 2. So since we are to obtain the value of the common ratio, we make R the solution of formula. So we make R the solution of formula. We are going to have R equals minus 2 plus 1. And minus 2 plus 1 will give minus 1. So the value of the common ratio R equals minus 1. Therefore, the common ratio of a geometric progression whose sum to infinity is minus 1 over 16 and first term is minus 1 over 8 is minus 1. So now if you want to check if this is correct, you can just write down the formula for sum to infinity. You substitute the value of A and R and see if we are going to get minus 1 over 16. So that solves the third question. Now we move to the solution of the fourth question. In the fourth question, we were told that the sum of the first three terms of a geometric progression equals to half its sum to infinity. So we should use this information to obtain the value for the common ratio of that particular geometric progression. So this is the statement of the question. The sum of the first three terms equals to half its sum to infinity. So this can also be written as twice the sum of the first three terms equals sum to infinity, and that is tagged as equation A. From the knowledge of the sum of the first n terms of a GP, so we are conversant with the sum of the first n terms of a geometric progression, which is given by the formula S subscript n equals A into 1 minus R raised to power n over 1 minus R. Then you know in the statement we have S3, which is the sum of the first three terms. So wherever you see n, you substitute it with 3. S3 will be equals to A into 1 minus R raised to power 3 over 1 minus R. And that is tagged as equation B. Also in the statement we have sum to infinity, and the formula for sum to infinity equals A over 1 minus R, which is tagged as equation C. So now, substituting B, that is the sum of the first three terms, and C, the sum to infinity of that particular geometric progression, into A, which is the statement of the question. So we have 2, in the statement we have 2 S3 equals S infinity. So now S3 is B, so we have 2 multiplied by A into 1 minus R cubed over 1 minus R equals A into 1 minus R. So we can cross multiply. If we cross multiply, we have 2A into 1 minus R cubed multiplied by 1 minus R equals A multiplied by 1 minus R. So we should divide both sides by 1 minus R. We are left with 2A into 1 minus R cubed equals A. So now we can divide both sides by 2A also. We divide both sides of this by 2A. We are left with 1 minus R cubed equals A over 2A. A, we cancel A, we are left with 1 over 2. So 1 minus R cubed equals 1 over 2. So since we are to obtain the value for the common ratio, we first made R cubed the subject of formula. So if we want to make R cubed the subject of formula, we transfer R cubed to this side and bring half to this side. If R cubed is transferred to this side, it changes to positive R cubed equals 1. If this is brought to this side, we have minus half. R cubed equals 1 minus half, which is half. So now we have the value for r cubed equals half, but we are to obtain the value for ordinary r, not r raised to the power 3. So as we all know, to eradicate cube root, we take cube roots of both sides. If you take the nth root of a number, is same thing as writing that number raised to power 1 over n. So if you take the cube root of r cubed, it's like writing r raised to power 3, everything raised to power 1 over 3. And according to the rule of indices, r raised to power n multiplied by 1 over n is same thing as writing r raised to power 1. So r raised to power 3, everything raised to power 1 over 3 is same thing as writing r raised to power 1, which is r, equals taking the cube root of 1 over 2. I know cube root of 1 is 1, because if you should multiply 1 thrice, you still have 1. So that is why cube root of 1 is 1, and you can just write cube root of 3. If you have cube root of 1 over 2, you can split it as cube root of 1 over cube root of 2. So cube root of 1 is 1 over cube root of 2. So if we take the cube root of both sides, we will have r equals 1 over cube root of 2. So now we have the value for the common ratio of that particular geometric progression that has the sum of its first 3 terms equals to half its sum to infinity. Therefore, the common ratio of a geometric progression whose sum of first 3 terms equals half its sum to infinity is 1 over cube root of 2, or you can say 1 over 2 raised to power 1 over 3. So that solves the 4th question. Now we move to the solution of the 5th question. In the 5th question, we were given a geometric series. The series 3 plus 2 plus 4 over 3 plus 8 over 9 plus 16 over 27. So we are asked to obtain the sum to infinity of that particular series. So from the series, the first thing we have to do is to identify the first term a and obtain the value for the common ratio r. So the first term in that series is 3, since it is the first number in the series. So to obtain the common ratio is 2 over 3, and it is obtained by dividing the second term 2 by the first term, which is equals to dividing the third term 4 over 3 by the second term 2, which is also equals to dividing the fourth term 8 over 9 by the third term 4 over 3, which is also equals to dividing the fifth term 16 over 27 by the fourth term 8 over 9. If each of this is evaluated, we have the value 2 over 3. Therefore, the common ratio of that particular geometric series is 2 over 3. Now, we have the parameters to obtain the sum to infinity of that particular geometric progression, and the formula for sum to infinity equals a over 1 minus r. So substituting the values of a and r into s infinity to obtain the value of s infinity. So now s infinity will be equals to a, which is 3 over 1 minus 2 over 3, which is the value of r. 1 minus 2 over 3 will give 1 over 3. So we have 3 divided by 1 over 3, which is equals to 3 multiplied by 3 over 1. And 3 multiplied by 3 over 1 will give 9. Therefore, the sum to infinity of the geometric series is 9. The sum to infinity of the geometric series 3 plus 2 plus 4 over 3 plus 8 over 9 plus 16 over 27 up to infinity is 9. So that solves the 5th question. Now we move to the solution of the 6th question. This 6th question is very similar to this 5th question. So in the sixth question, we are given in the sixth question we are also given a geometric series in form of decimal. So we identify the first term in that series as 0.5, which can be written as 5/10 when converted to a fraction, and 5/10 is same thing as writing half. So now we obtain the value of r by dividing the second term by the first, which is like 5/100. 0.05 when converted to fraction is 5/100 divided by 5/10, which is 5/100 multiplied by 10/5, and that will also give 1/10. And dividing the third term by the second term, which will also give 1/10, which must also be equals to dividing the fourth term by the third term. And if all of this is evaluated, we have the value 1/10, or when converted to decimal, we have 0.1. Now substitute the value of a and r into s infinity, and the formula for s infinity is a/1 minus r. So if we substitute the value of a and r into that, we have the value of a, which is 1/2/1 minus the value of r, 1/10, or we write it in decimal, 0.5/1 minus 0.1. And here we will simplify this. We have 1/2. 1 minus 1/10 we give 9/10, or 0.5 and 1 minus 0.1 we give 0.9. So if we should evaluate this, we have 1/2 divided by 9/10, which is equals to 1/2 times 10/9. So 2 will divide 10 in 5 places. So we have 1 multiplied by 5 to get 5, and 1 multiplied by 9 to get 9. Or 0.5 divided by 0.9 we give 0.5555556 when we write it to 7 decimal places. Therefore, the sum to infinity of this series is either 5/9 when written in fraction, or 0.55556 when written in decimal to 6 decimal places. And that solves the sixth question. Now we move to the seventh question. This seventh question is in form of trigonometric because we have the cosine. So from the series, from the sequence, the first term a is 1, and we are to obtain the value of the common ratio. So for the common ratio, we have cos 60 degree, and that is obtained by dividing the second term cos 60 degree by 1, which is equals to dividing the third term cos square 60 degree by the second term cos 60 degree. And if each of this is evaluated, we have the value of the common ratio equals cos 60 degree. So we substitute the value of the first term and common ratio into the formula of the sum to infinity. So we have s infinity equals 1 divided by 1 minus cos 60 degree. So if you are very conversant with the trig table, that is the trigonometric table, you know the value of cos 60 degree is 1/2. So we have 1 divided by 1 minus 1/2, and 1 minus 1/2 we give half. 1 divided by half is equals to 1 multiplied by 2/1, and 1 multiplied by 2 we give 2. Therefore, the sum to infinity of the sequence 1, cos 60 degree, cos square 60 degree, and so on is 2. And that solves the seventh question. So this is the end of the solution of the questions. And also we have exercises for you to solve to check if you really understood what we have been explaining. So we have some exercises from the UTME past questions. So we have 5 exercises in all. Next video will be on statistics with sample questions and solutions. Please subscribe to our YouTube channel, like and share our videos. Thank you.